All right, today we're going to trace the explosive origins of an idea that honestly shapes our world every single day. We're talking about the birth of statistical thinking. Welcome, everyone, to the Flow Tao Salon. This is the place where we get into the really big ideas, the ones that basically define our reality. It all starts with something we totally take for granted. Think about it. We talk about the average salary, the average height, the average customer. But have you ever stopped to wonder where that idea even came from? How did we go from just a bunch of numbers to these powerful charts that could literally save lives and build entire empires? So to get this story, we've got to go back to the 18th and 19th centuries. This was a time when there was this massive, and I mean massive, explosion of data. All of a sudden, governments and scientists were collecting numbers on, well, everything. Births, deaths, trade, crime, you name it. And this created a huge problem. I mean, can you imagine trying to understand your country's entire economy or figure out a disease outbreak just by reading thousands and thousands of pages of tables full of numbers? It would be totally overwhelming, right? Any real patterns, any useful insights were just completely buried in this sea of digits. Okay, so this slide just perfectly captures the revolution that happened. On the left, that's the old way, a super dense table of deaths in Vienna. I mean, yeah, the information is there, somewhere, but it's almost impossible to grasp quickly. Now look at the right. This is the genius of a guy named William Playfair. In one single glance, you can see centuries of economic history. You can see the relationship between the price of wheat and what a worker was getting paid. It's night and day. And Playfair, he was just getting started. With this chart, he took something really abstract, a trade balance, and made it completely visible. You see that space between the two lines? That's imports and exports. You can instantly see when England was making a profit and when it wasn't. For economists and politicians back then, this was like having a new superpower. And this brilliant idea, it wasn't just for money and trade. Look at this. This is a map of cholera deaths in a city called Exeter. By putting a little red mark for every single death, a doctor named Thomas Shapter could literally see the disease. He could see it clustering in certain neighborhoods, revealing these patterns that were just totally invisible when you were just looking at a long list of names. So, okay, we've got all this new data and these amazing new ways to actually see it. So a new question starts to pop up. What if you could find predictable laws for, well, for us, for human society itself? This question brings us to a really pivotal figure, a guy named Adolf Kepler. Now, before Kepler came along, people were already trying to find some kind of order in the chaos of society. You had guys like Sussmilk, who looked at the super predictable rates of birth and death and said, see, that's proof of God's divine plan. And then you had others, like the famous Thomas Malthus, who argued that no, society is governed by these brutal, unforgiving natural laws, like the fact that population is always going to outgrow the food supply. But then came Quetelet. And remember, he was an astronomer. He was used to thinking about planets and stars. He took this whole thing a radical step further. He started looking at crime statistics, and what he found just blew his mind. Year after year, the number of murders, the number of forgeries, even poisonings, it was all shockingly predictable. He thought this was proof that society wasn't random at all. It operated like a machine. He even called it social physics. So how do you understand this social machine? Well, he borrowed a tool from his day job, from astronomy. See, when astronomers take a bunch of measurements of a star's position, the data always forms this perfect bell-shaped curve. They called it the error curve, and the very peak of that curve was thought to be the star's one true position. So Quetelet had this wild idea, what if you could do the exact same thing, but for people? And that led him to invent his most famous and maybe most controversial concept, l'homme moyen, which is French for the average man. His argument was pretty simple but profound. He said if you measure any human trait across a whole population, height, weight, even something as complex as a propensity for crime, the data would fall into that same perfect bell curve. But here's the kicker. For Quetelet, that peak, the average, it wasn't just a mathematical middle. He believed it was the ideal, the perfect type that nature itself was aiming for. And you can see his method right here in action. He literally took the chest measurements of 5,738 Scottish soldiers and crunched the numbers to fit his beloved bell curve. And just like that, in one single move, almost 6,000 unique individual men were just transformed. They became a single abstract ideal. Every single thing that made them different from one another was now just a statistical error on the way to the perfect average. But what if those errors weren't errors at all? What if all that variation, all the ways people are different from the average, what if that was actually the most important part of the whole story? This, right here, is where our narrative takes a really crucial turn. This is where another brilliant thinker, Francis Galton, steps into the ring. And he basically takes Quetelet's big idea and flips it completely on its head. Where Quetelet looked at the average and saw perfection, the ideal, Galton looked at it and saw mediocrity. For Galton, the real action wasn't in the middle. It was out on the edges, in the variations, the extremes. That's where you were going to find genius, real talent, and the secret keys to understanding heredity. So as Galton was studying how traits get passed down from parents to kids, he discovered something really fascinating and super powerful. He noticed that the children of extremely tall parents, well, they weren't usually even taller. They were still tall, for sure, but they tended to be a little bit closer to the average height. And guess what? The exact same thing was true for the children of very short parents. He gave this phenomenon a name: regression to the mean. And check this out. This is how he visualized it. On the left, that's a device he invented called a quincunx. It just drops little beads through a bunch of pins. And no matter what, they always form that perfect bell curve at the bottom. It was a beautiful way to show how randomness can actually create order. Then, on the right, he's using real data. He plotted the heights of parents against the heights of their adult kids. You can see that distinct oval shape, which was the mathematical picture of his regression idea. It was like he discovered a statistical law of heredity. But this intense focus on heredity, on measuring every human variation, it had a really dark side. Galton's new science of statistics would unfortunately give birth to a social movement with absolutely devastating consequences. Galton himself founded this movement. He called it eugenics. And the logic, you can see how it followed directly from his work. If desirable traits like intelligence are passed down, and undesirable traits are too, then, the thinking went, you could improve society by encouraging the fit to have more children and preventing the unfit from doing the same. Now, this wasn't just some fringe academic theory. It became actual state policy all over the world. In the United States, more than 60,000 people were sterilized by court order. Similar programs were running in places like Sweden, Norway, and Japan. And of course, in Nazi Germany, this ideology reached its most horrific conclusion, where the state sterilized around 400,000 people they deemed unfit before it escalated into mass murder. Okay, that history is heavy and it's really important to sit with, but it's essential we talk about it because these ideas, the average, the chart, the variation, they didn't just disappear. Not at all. They evolved. And today, they are the invisible architecture of our modern world, especially when it comes to business. So let's connect all these historical dots to today with 3 key takeaways. Takeaway number 1. Quetelet's average man is the direct ancestor of the average customer. I mean, think about it. The entire concept of a target demographic, a marketing persona, a user profile, it's all built on that exact same foundation. It's about boiling down immense human variety into a single, manageable, average ideal that you can design a product for and then sell to. All right, takeaway number 2. You're looking at the ancestor of every single business dashboard you have ever seen. This incredible chart was made by Florence Nightingale. And with it, she proved to the British government that way more of their soldiers were dying from disease in the hospitals, that's all those big blue wedges, than they were from actual combat. It's such a powerful argument in just one image, and it established a core business principle we use every day. Compelling data visualization drives action. And that brings us to takeaway number 3. The power of variation. Look, businesses love the idea of the average customer, but the smartest companies, they follow Galton's lead. They know the real opportunity isn't just smack dab in the middle of that bell curve. No, it's out in the variations. It's in the niche markets, the early adopters, the power users. Understanding the full spectrum of your customers, that's how you find your next big thing. So when you think about it, we've gone on this incredible journey. From Quetelet's ideal average man to Galton's focus on crucial variations, these concepts went from simply describing the world to actively defining it. They shape the products we buy, the markets we operate in, and even how we see ourselves. And you know what? This story is far from over. The only real question is, as our data gets more and more powerful, what are we going to let it define next?